In this video, I will be talking about problem 1 from 2018 at the Canadian Mathematical Olympiad, CMO. Okay. For those of you who don't know, CMO, so Canadian Mathematical Olympiad, is an invitational contest in the sense that Canadian students write COMC, which stands for Canadian Open Math Challenge. Those of them who do the best get to write CMO, and then from those students, they make up the national team of Canada, who eventually writes the IMO, the International Mathematical Olympiad contest. All right. Now, in the description of this video, I wrote the text of problem 1 from 2018 CMO. Basically, the problem says the following. Consider a set of tokens in the plane. I have here a diagram of tokens T1, T2, and T3. So given a set of tokens in the plane, we consider this collapsing process. And in this process, we take two tokens, in this case T1 and T2, and we move them both at the midpoint of the segment determined by the original positions. Okay, and then we repeat the process. We take some other two tokens and we collapse them, and then so on and so forth. Okay, and a family of tokens is called collapsible if there is a finite process by which all the tokens are moved into one point. All right, so the problem says show that a family of n tokens is collapsible if and only if n is a power of 2, so n is of the kind 2 to the power of k, where k is a natural number. Now, so this is sort of the geometrical view of the problem in case we have three tokens, T1, T2, and T3. All right, but see, these tokens keep changing their positions. So I believe it's a good idea that we associate a system of coordinates with this problem. Okay, so instead of talking about token T1, okay, maybe originally we have token T1 of coordinates x1 and y1, token T2 of coordinates x2 and y2, right? So this collapsing process takes these two tokens and then it moves T1 at the point of coordinates x1 plus x2 over 2 and y1 plus y2 over 2, and it does the same with T2. So sort of this is the algebraic view of the process of collapsing two tokens. All right, if this is a very simple, very nice geometrical view, this is just equally simple. The notation, again, the notation is more complicated, but nothing more than that. Okay, now so the problem is to show that two statements are equivalent here. So a family of n tokens is collapsible if and only if n is a power of 2. Okay, in this particular video we will be showing that if we have a family of 2 to the power of k tokens, then we can collapse it. All right, now most of the time if a problem is let's say serious, you may want to get some intuition for it. Okay, so for example, if we have a family of two tokens T1 and T2, how do we collapse this family? Well, this is such a simple problem that okay, the only thing we can do is take the midpoint of the segment determined by T1 and T2 and move the tokens at that point. So unfortunately this is so simple that there is not much we learn from this process. All right, how about we take 4 tokens? Okay, because again we are only going to be looking at n a power of 2. So if we've got 4 tokens, T1, T2, let's say here T3 and T4. Okay, how do we collapse these tokens? Maybe you can pause the video and see if you can figure out a way to collapse these tokens. Okay, the way I would collapse them is the following. I would take maybe T1 and T2, all right, and okay, move them at the midpoint, right? So T1 and T2 get moved here. I would take T3 and T4, collapse them. All right, so T3 and T4 get moved here. Okay, and now what I would do, I would take T1 and T3, collapse them here. Okay, T1 and T3. I would take T4, T2 and T4, collapse them. T2 and T4. So now all of a sudden, all my 4 tokens are collapsed at some point. Now, I believe I learned quite a bit from this process here. Okay, so now I actually believe I have an algorithm to collapse families of tokens. All right, so what I will do, I will solve this problem by actually setting up an induction, mathematical induction. So I would say P of n is this particular sentence. Any family of 2 to the power of n tokens is collapsible. Okay, so this is my statement, and I will try to prove that this statement is true by using mathematical induction. Okay, as discussed in a previous video, mathematical induction involves 2 steps. Step number 1 is typically called verification step. Okay, so basically this involves only us proving that P of 1 is true. Well, P of 1 is true, we just showed it here. Okay, there's not much to discuss about it. Sure, you are supposed to write that down in a couple of sentences if you actually write the contest. All right, you can actually, what we did here, we actually figure out that P of 2 is true. You don't have to do it, but we did it, so I'm just going to write it down. All right. Now, the second step of mathematical induction is the inductive step. Okay, so which means that assume P of n is true for some n natural number and prove P of n plus 1 is true. All right, so let's assume that P of n is true, and let's see how we can prove that P of n plus 1 is true. Well, in order to do so, let's say that A be a set of tokens. Okay, T1 a token that's of coordinates x1 and y1, T2 of coordinates x2 and y2, and so on and so forth. The last one, okay, we want a family of, because we are looking at P of n plus 1, we want a family of 2 to the power of n plus 1 tokens. So the last token would be T 2 to the power of n plus 1 of coordinates x 2 to the power of n plus 1 and y 2 to the power of n plus 1. All right, so this is a family of tokens of 2 to the power of n plus 1 tokens. Okay, how about we do this? How about first collapse T1 and T2, collapse T3 and T4, and collapse the last 2 tokens, T2 to the power of n plus 1 minus 1 and T2 to the power of n plus 1. All right, so if we collapse tokens in pairs like so, as you notice, just like we did when we looked at P of 2, we collapsed T1 and T2 first and T3 and T4 second. Okay, so what we get is we get a family B. Okay, and now T1, just because of this collapsing, is going to have coordinates. Okay, so we collapse T1 and T2, so it's going to have, T1 is going to have coordinates x1 plus x2 over 2, y1 plus y2 over 2. Okay, and T2 it's gonna have the exact same coordinates. x1 plus x2 over 2, y1 plus y2 over 2, right? Then t3 and t4 will have their own coordinates, okay? But I hope we get the idea. All right, sure, if this were to be a real proof, it's probably a good idea to write more, but I'm restricted to sort of using a limited amount of space. All right, so but this family, original family of ours, becomes this family once we collapse pairs of tokens. Okay, now how about we look at two more families, C. Let's say C is T1 of coordinates x1 plus x2 over 2 and y1 plus y2 over 2, and then T3 of its own coordinates, and so on and so forth. So we take only the tokens with odd index, okay, and the family T2 of coordinates T4 of its own coordinates, and so on and so forth. All right, well, what do we notice about these two families? Okay, so first of all, because of the fact that here we took only the tokens with the odd index, so this is a family of 2 to the power of n tokens, and the same is true for D, is a family of 2 to the power of n tokens. All right, what else do we notice? Well, T1 and T2 actually have the same coordinates. We wrote them here. T3 and T4 have the same coordinates. All right, so actually these are two identical families of tokens of size 2 to the power of n. All right, so now our inductive hypothesis says that P of n is true. So this family, C, can be collapsed into one point. But C is the same as D. Just the naming of the tokens is different, but their positions are the same. All right, so we can collapse C according to our inductive hypothesis, and according to the same algorithm, we can collapse D. Okay, so now putting the two together, we can collapse B. So we actually ended up collapsing A. So mathematical induction helped us prove the fact that every single family of size 2 to the power of A can be collapsed.